Now you can start.
Okay, so welcome everyone to today's seminar of this Bhaskaracharya Pratishthan talk on triangle groups, Bailey uniformization and modularity. So today's speaker is Professor Shaunak from Indian Institute of Science, and he will be speaking. He'll be giving second talk on modular curves. So Shaunak, it's all yours.
So thank you, Somnath, for the invitation, and thanks organizers again for inviting me for this talk. So today we are going to see modular curves part 2. So this is a sequel to the talk I gave like 3 weeks ago, around 3 weeks ago. So the main aim of the talk of this series of the series of 2 talks is to introduce to modular, give an introduction to modular curves, and state various versions of modularity, and we'll try to explore connections between them. Obviously, even the proving modularity theorem is a very hard thing, and also like exploring the connections is also not very trivial, especially in a limited time. Obviously, in a semester-long course, we can do all of that. So what I'll do today is I'll continue from where I left off last time, after a brief recall, and then I'll talk about these various modularity theorems, various versions, and try to connect them with each other. I may not be very precise all the time, and most of the time I'll just give an outline, and I may have to improvise depending on how much time I have. So let's begin. But yes, the main aim is to basically look at these modularity theorems, which I had stated a couple of versions last time, but now I'll state more versions and I'll try to connect them with each other. So recall. So modularity, so we were interested in looking at modularity theorem, and a rough version I had given last time was the following. A rough statement, if somebody asks you a slogan, what's a modularity theorem? A slogan or a rough statement would be that all rational elliptic curves arise from modular forms. Now, obviously, this is, this sounds good as a slogan, but this is not precise at all. All rational elliptic curves arise from modular forms. So obviously, we want to be more precise, and later on, as we proceed in this talk, we will make this statement more precise. But this is like a one line that you should keep in mind about modularity theorem. If somebody asks you, this is sort of the what you can say, the slogan. And this was first conjectured by Taniyama and Shimura, and it was proved by Wiles while proving. Many of the cases were proven by Wiles during proof of Fermat's theorem. So includes the work of Taylor-Wiles as well. And then final blow came with this joint work of Broy, Conrad, Diamond, and Taylor. So they proved it in complete generality. Of course, then there is obviously this, you can ask more questions like what about elliptic curves or number fields and all, and there these modularity theorems are wide open, and it's a very active area of research. So if you remember last time, I had started giving some precise statements of these modularity theorem. So to begin with, if you remember the notation, x naught of n was modular curve of level gamma naught of n. And the first version was, I called it XC. So what we are going to do is we are going to give these versions on complex numbers first, and then we'll move on to the algebraic curve setting where we'll give the versions over Q. And then we'll also, while doing this, we'll also try to connect it with modular forms more explicitly. Okay, so the first version that I had stated was this modularity theorem, version XC. So this C will keep on denoting that we are over complex numbers. So this is like a Riemann surface version and not algebraic curve version yet, but we will see algebraic curve version as well. So it says that let E be a complex elliptic curve with rational J invariant. So the J invariant is rational. Then for some integer n greater than 0, there exists a surjective holomorphic function of compact Riemann surfaces. And we call this Fe, and this function goes from, or this map goes from x naught of n, and I'm going to write C here so that you know that this is Riemann over C to E. Okay, so you get a complex elliptic curve with a rational J invariant. Then for some n greater than 0, we have a holomorphic function from x naught of n to E. This is the first version. You know, this is the version I had stated last time, and this Fe is called modular parameterization of E.
0n is not a compact Riemann surface.
Sorry?
No, x0n is not a compact Riemann surface. I think this.
No, x0n is a compact Riemann. We had this discussion last time also, that you can define the charts. You know, this was given in Mihir's talk, that x0n, you can give the charts to make it a compact Riemann surface. So we had this same discussion last time as well.
Oh.
Called the modular parameterization of E. Now, there is an equivalent version in terms of Jacobians, which I also sort of stated last time. So let me state it now first. I did not prove that they're equivalent, so I'll give a sketch of the proof of equivalence. So let J naught of n be.
No, could you recall for me how do you make x0n elliptic curve for all n?
No, x naught of n is not an elliptic curve. There is, so this theorem says that there is this map from x naught of n to E.
Yes.
Given an elliptic curve, there is a map, but I'm not going to prove the theorem. The proof is very hard.
But you said holomorphic function of compact Riemann surfaces.
Yes.
So it suggests x0n is a compact Riemann surface.
It is. So yeah, you can define charts around it. You know, this was done in last semester Mihir's talk. I mean, I don't remember it at the top of my head, but you just define charts around each point, and you can do it. You know, this is explicitly given. So you can diamond Schurman, for example. You know, it is given there.
Okay, all right.
So moving on. So J naught of n is the Jacobian of x naught of n, which I had defined last time. So this was just, you take holomorphic differentials, the dual of holomorphic differentials, and then you go modulo h1 of x naught of n z. This is the first homology group, and we had seen how this goes inside this last time. And Abel's theorem said that this was isomorphic to pic 0. Pic 0 of x naught of n, where pic 0 is basically degree 0 divisors modulo divisors coming from meromorphic functions. So let me just write it down. These are degree 0 divisors over x naught. These are divisors of meromorphic functions. So this is isomorphic to pic 0. And because of this is Abel's theorem, we can actually, you know, use this pic 0 as the definition of Jacobian, and then we can define Jacobian over for any algebraic curve and so on. So we'll be using this. And maybe a remark would be that, remark is that a Jacobian is, this is an abelian variety. So then we can, we can take, we can state this modularity theorem in terms of this Jacobian as well. So modularity theorem version Jacobian, that let E be a complex elliptic curve with rational invariant then for some integer n greater than 0, there exists a surjective holomorphic homomorphism of complex tori. So this is phi e, J naught of n to E. So because J naught of n is an abelian variety over C, it's a complex torus, and E is also the same. So this is a sort of a holomorphic homomorphism of complex tori. So this is a reformulation of modularity theorem in terms of Jacobian over complex numbers. And actually the versions are equivalent, the XC and JC, these versions are equivalent. So let me try to give a quick sketch of why they are equivalent. So suppose you have version JC, which means there is a map from the Jacobian to E, and then we want to find out there is a map from the modular curve itself. So let's look at version JC implies version XC. So for this proof, basically, since E is in the image of this Jacobian, or E is the image of Jacobian, I should be more precise here, sorry. So E is the image of J naught of n under phi E. This means this Jacobian itself is non-trivial. J naught of n is non-trivial. But this means that the genus of so genus G of x naught of n is greater than 0, because if the genus is 0, then the omega 1 has dimension 0, so Jacobian is sort of trivial. So basically this means that the genus is 0, and then we have a map from x naught of n. So this x naught of n, because the genus is greater than 0, the x naught of n sort of embeds into j naught of n. The map is simple. After fixing a base point, you have to fix a base point. X naught in x naught of n. Okay. Sorry, I am being a bit, after fixing a base point x naught in x naught of n. We have this map which sends x to the divisor of x minus x naught. And because as genus is greater than 0, so call this map I. This I is an embedding, because there is no degree 1 meromorphic function by Riemann-Hurwitz formula. So I is an embedding, as there is no degree 1 meromorphic function on x naught of n by Riemann-Hurwitz formula. So basically now what has happened is that we have an embedding of x naught of n in Jacobian, and we have a map from Jacobian to E. So we compose it. So composing this embedding I and this map phi E, we get a map from Fe from x naught of n to E. Okay, and now if you see this pick 0 definition tells us that sort of j naught of n is generated by image of I, and image of I also contains 0. Because you look at the I of x naught, so I of x naught is actually 0, because it is x naught minus x naught, and all the degree 0 divisors are just generated by the points of the form x minus x naught. So image of j naught of n is generated by image of I. So this means that image of Fe contains 0, so 0 is here, and image of Fe is not 0, as phi E is surjective and image I is generating j naught, right? Because image of I is generating j naught of n. So if all the elements of x naught are getting mapped to 0, that means all the generators are getting mapped to 0 under phi E, which means phi E is 0, but that is not true. So therefore, if the map Fe is not 0 and it contains 0 and it is not 0, which means it is non-constant. Fe is non-constant, which means it is surjective. So this is one direction where JC implies XC. And now we go to XC implies JC. And for this also, this is also again slightly, you can say it's an easy argument in a sense. So, an outline is easier to see. So you have a map FE from, so basically you are given a map from FE from X0 of n to E. And now you have to cook up a map of say surjective holomorphic homomorphism from Jacobian to E. So this basically induces a map between Jacobians. You call it FEJ. So whenever you have a map between two curves, you get a map between Jacobians very easily. So this is J0 of n, and Jacobian of E is actually just E. And this map is simple to describe. An element looks like some nxx. It goes to some nx fe of x. So this is FEJ, and you can also have a map in the reverse direction, FEJ from E to J0 of n. So this is again between Jacobians, but Jacobian of E is E because E is an elliptic curve. So you have something like summation nyy. It goes to summation ny times summation ex x, where so x is in Fe inverse y, and this ex is the ramification index. So we can say that ex is multiplicity of Fe at x in a neighborhood of x. So in a neighborhood of x, Fe is ex to 1. Okay, just so that you know what ex is. Now, if you compose these two, again, an easy exercise would tell you that the composition is just multiplication by degree of Fe. So this is a surjection because it is between E to E and it is multiplication by an integer, which is a surjection. So this means FEG is a surjection. FEJ is a surjection. Which is what we wanted. This was the map. We wanted a map. So this is a map. This is a holomorphic homomorphism, and all we wanted to prove is that it is surjective. And this just tells us that this is a surjection just by looking at composing these two groups. So this tells us that the Jacobian version and the version over X, they are the same. So getting a map from X0 is same as getting a map from the Jacobian, but we have to be careful that the map from the Jacobian is going to be a homomorphism. But in general, X0 of n is not an abelian variety, right? It's not an elliptic curve in general. So therefore, in that version, that is just a holomorphic map. But in J0 version, it is a map of, it is a homomorphism as well. So it's a map of abelian varieties as well. There is one more version that we can get from J0. So for that, let me, maybe I can recall a bit from Mihir's talk on Aishla Shimura. So we have an action of Hecke operator on this Jacobi, So J0 of n, this has an action of Hecke operators. So Hecke operators, these are the ones they are sort of acting on modular forms, and they can be defined using lattices, and then you get an action on the modular curve, and then you can extend it. It's not an action on modular curve; it's like a correspondence, and you extend it to J0 of n. So J0 of n has an action of Hecke operators Tn with n positive integer. So n belonging to z greater than 0, and we let Tz be the Z algebra generated by Hecke operators Tn acting on, but now they are acting, so here in Tz, they are acting on S2 of gamma naught of n. So this is a space of weight to forms, of weight to cusp forms of level gamma naught of n. So basically what in Mihir's talk you saw that J naught of n has an action by this Tz. So J naught of n has an action by Tz. And this is because, if you see as omega 1, if you see this omega 1 holomorphic, so you take differentials on x naught of n, this is nothing but S2 of gamma naught of n, because these are just the these are just the differential, holomorphic differential forms on x naught of n, because the weight here is 2. And so therefore the action of the Hecke operators on S2 will give you action on its dual, and that's how you get the action on J naught. Now let F be a weight 2 eigenform of level gamma naught of n, be an eigenform for all Tn, where n is just an integer. We are not taking the hypothesis that n is co-prime to big N or something. Then, we have a ring homomorphism. Call it lambda f from Tz to C, which sends a Hecke operator Tn to Tn eigenvalue of f. And we let IF be, so this is a bit of a notation that I'm writing, because it will be used in stating another version of modularity theorem. So we let IF be the kernel of this map lambda f, and kf be the number field generated by eigenvalues of f. So first of all, we know that, I should say Hecke eigenvalues. We know that the Hecke eigenvalues of f are all algebraic integers, and they generate they are all contained in a finite extension. So this is indeed a number field. So this is a number field generated by Hecke eigenvalues of f over q. Okay, and so this is a notation, and then I would like to give one more sort of a factoid, which I'm not going to prove because I don't have time, is that suppose f is some an q power n. I look at its q expansion. N goes from 1 to infinity because it's cos form. So suppose f is inside this space S2 of gamma naught of n, and this is an eigenform. Now you know that all these an's, they are inside this kf, and kf can be embedded in C in many possible ways. If kf is not q, there are more than one ways in which you can embed. So suppose sigma from kf to C is an embedding, then obviously I can apply sigma to f, and I can ask, right? I can just apply sigma to all the coefficients of f, and I would like to know what that is. Then it turns out that that is also an eigenform of same weight and level. Then f sigma, which I define to be some n goes from 1 to infinity, sigma of an q power n. This is also in S2 of gamma naught of n, and this is also an eigenform. And if f is a new form, that means it is not coming from a lower level, then so is f sigma. If f is a new form, then so is f sigma. Now you would be wondering, why am I doing all this? Why I suddenly changed from Jacobian to abelian to this cus forms, modular eigenforms. That's because I'm going to now use this, given an eigenform like this, I'm going to now use it to construct a quotient of my Jacobian, which I can because this Jacobian is closely related to weight 2 modular forms, as I had said above. So therefore, now we so suppose again f is an eigenform for all Tn. So f is in S2 of gamma naught of n, be an eigenform for all Tn. Then I let AF to be this quotient. J naught of n also has an action of this Hecke algebra. So I can go modulo the quotient by IF. IF is the ideal, which is given by sort of the kernel of the map given by F. So I can take AF to be J naught of n modulo IF of J naught of n, because J naught of n has an Hecke action. IF of J naught of n makes sense. And then this is called the abelian variety associated to F. So this is called the abelian variety associated to F. And now I can state a conjecture, the modularity theorem in the language or in terms of this abelian variety, in terms of this abelian variety associated to cusp forms. So we call this abelian variety associated to F. And now I'm going to sort of give you modularity theorem version in terms of this abelian variety, this quotient of Jacobian. So I'm going to call it AC. So modularity theorem version AC. So what does this version say? Again, let E be an elliptic curve. Sorry, I'm repeating this statement, but since all the statements include this sort of slogan line, I have to repeat. But let E be an elliptic curve, elliptic curve over C with rational J invariant. Then what this theorem, this version says is that then for some integer n greater than 0 and some new form, so that means there exists an integer n greater than 0 and a new form f of weight 2 and level gamma naught of n, there exists a surjective holomorphic homomorphism of complex tori. And this homomorphism, it goes from AF, which is the quotient of J naught that we got from F, to E. So maybe I should put a box around it. So, this, one may think that this is sort of a refinement of what we just saw, because we said that in the J naught version, it said there is a surjective holomorphic homomorphism from J naught. And here it is telling us that there is a surjective holomorphic homomorphism from this abelian variety AF. Okay. Again, this J naught and this version, they are also the same versions, so getting a holomorphic homomorphism, surjective holomorphic homomorphism from J naught of n to E, it's same as getting a surjective holomorphic homomorphism from one of these, at least one of these quotients AF. So let me give you maybe a very quick sketch. It's not precise at all. So let me try to give you a very quick sketch of why this is true. So version JC implies version AC. So here the big hammer in this case is that we have an isogeny from J naught of n to okay, wait. What did I? Okay, no, nothing, which is good. I'm yet to define that notation. Okay, sorry. So, continuing. So we have an isogeny from J naught of n to direct sum of these quotients AF power MF. And now what is this direct sum over? So the direct sum is over equivalence classes. I have not defined what these equivalence classes are. Just give me a moment and I'll define. So the sum is over equivalence classes F of new forms, F of level gamma naught of M and weight 2, okay, where M divides N. And this MF is a number of divisors of n over m. So maybe I should say, maybe I should write an f somewhere so that it makes sense that everything is depending on f. So this is gamma naught of mf, and this is mf, and this is mf. So basically, the point is that, let me just, yeah. So if f is an eigenform, then this equivalence class is defined to be the set of all f sigma, where sigma is an embedding. So what this statement is telling us is that J naught is isogenous to this product of quotients that you get. You take all new forms which are coming from a level dividing n, and you take basically the equivalence classes of them. So weight is fixed to be 2. Now you vary level over divisors of n, and for every divisor you take equivalence classes of new forms that appear there. And then you take the copies of those abelian varieties AF corresponding to that, and the number of copies is the number of divisors of n over nf. So basically on right hand side, on left hand side you have this Jacobian, and on right hand side you have a bunch of quotients of it, and you take their direct sum, where multiplicity is given, the sum is given over, is done over new forms of level dividing n, and so on. And the claim is that these two objects, they are isogenous. I mean, obviously there is a map from J naught to that, but then it's all surjective and so on. So this is a claim that I'm not going to prove again because I am a bit pressed for time, but you can say that very roughly, the claim follows from the fact that you can use new forms of lower level to get a basis of S2 of gamma naught of n. That S2 of gamma naught of n has a basis consisting of eigenforms of the form f of dz, where d divides n over, sorry, f is a new form of level mf dividing n, and d divides n over mf. So basically you can just take new forms, you can bump their levels, and that's how you get the eigenform basis of S2 of gamma naught of n. So you use this fact to sort of split your S2 into direct sum of subspaces which corresponds to each new form, and then you can construct the abelian varieties corresponding to that. And then because Jacobian is just S2 dual of S2 modulo H1, and we have this direct sum of S2 into eigenforms given by this fact, we get this isogeny or the isomorphism. Okay. So basically, J naught of n is a product of these abelian varieties. You can I think it is true that these are isomorphic. So J naught of n is basically this product of these abelian varieties. I should say that even though I have glossed over this statement, or I have gone very fast over this statement, this is a statement of importance and of very much interest, because a lot of things sort of come out because of this. So I should probably put a bracket around this. It's not obvious at all, but very important. Okay, so now continuing our journey. So basically, now we want.
I suppose the degree of the map can be computed of this isogeny.
I think so. I think this is going to be an isomorphism, but unfortunately, I don't remember at the top of my head if it is an isomorphism, but a degree can certainly be computed. It's not hard. I mean, you just have to follow all the pieces and follow the computations. So I think degree can be computed for sure. And if I'm not mistaken, I think this is an isomorphism, but I'm not sure. Maybe I shouldn't say isomorphism, just say isogeny to be safe.
These AFs are even elliptic curves, right?
AFs are elliptic curves only when f is rational.
If If all the Fourier coefficients are rational numbers.
Yes. If all the Fourier coefficients of AF are rational, then AF is a elliptic curve. Otherwise, it is not. It's an abelian. So maybe I can also say
Nice.
dimension of AF. We actually know this. This is the degree of KF over Q. KF is the coefficient field.
Okay.
Okay, so we were proving that JC implies AC. So if we have a map from, so if we have a holomorphic surjective homomorphism from J naught of n to E, we can use dual of the isogeny that we got above. That we got above to get the map from this product AF power MF to E, and then each restriction is either constant or surjective, and each restriction to each restriction of this. So this is an holomorphic surjective homomorphism. And restriction of this map to each AF is also is either surjective or constant. But the whole map is kind of surjective. So it has to be, as the map is surjective, maybe I should call this something psi. The map psi is surjective. Psi restricted to AF should be surjective for at least some F. So this means that you have a map from AF to E, which is holomorphic surjective homomorphism. So this was the first direction. And if you want the second direction, it's even easier, I think, because you have a version AC implying version JC. You can say that this is even easier because if we have a holomorphic surjective homomorphism from AF to E for some F, then we can compose it with the surjective map. This surjective map, because this AF is a quotient of J naught, to get a map from J naught from J naught of n to E, which is holomorphic homomorphism, holomorphic surjective homomorphism. So basically, once you know this splitting of J naught into these abelian varieties corresponding to new forms, we know how this JC and AC, these versions are also equivalent. So we saw three versions over complex numbers. One was a surjective map from X naught of n to E. The other one was a surjective holomorphic homomorphism from J naught of n to E. And the third one was a surjective holomorphic homomorphism from AF to E. And all three of them, we just saw they are equivalent. Modulo some details. I have not given all the details, but I have convinced you that all these things are equivalent. But basically, another point is that all of this picture can be shifted to Q because X naught of n is actually an algebraic curve over Q. So again, recall from Mihir's earlier talk.
I think he proved that.
Yeah, he gave a Riemann surface structure to X naught of n, which made it a compact Riemann surface structure, which made it into an algebraic curve over C. And in fact, then he proved that it has a model over Q. It has an equation over Q. So this was, I think, sometime in October last year. So X naught of n. So this is an algebraic curve. And it is actually defined over Q. That is, it has a model over Q. Equation over Q. So now what we can do is we can state all these theorems, modularity theorems in the algebraic geometry language.
I think this theorem is in Mill's book, right?
No, in Mihir's earlier talk.
Mill, M-I-L-N-E.
Yes, it is there. I think it is there in Milne's book. Yes, it is also there in Diamond Sherman, I believe. But it is there in Milne's book, if my memory serves me correctly. You're right. So now we can, we can sort of state the algebraic versions of whatever we have done so far. So maybe a remark is that since x naught of n is defined over Q, this Jacobian, we can take its Jacobian over Q. We can take its Jacobian sort of over Q, because this Jacobian, you can use it, this pick zero thing, and which will tell us that which would mean that J naught of n is an abelian variety over Q, abelian variety defined over Q. So we are sort of shifting the picture over Q. And moreover, this also means that, and since the Hecke operators were also defined over Q, the quotients AF that you get of J naught, they are also over Q, because they are going modulo the action of Hecke operators, which is over Q. The abelian variety is AF, which are quotients of J naught of n by Hecke operators, by action of Hecke operators, I should say. They are also abelian varieties defined over Q. So basically now all of this, we can think of them as varieties over Q, J naught, X naught, this AF, everything. So abelian varieties defined over Q. So now let me state the algebraic versions of this conjecture. Now maybe I'll just sort of combine them together maybe. So modularity theorem, maybe I'll state them differently rather than being lazy. So this is version x cube. Okay, so let E be an elliptic curve over Q. And for some integer greater than 0, some integer n greater than 0. So this is like exactly the version that we had seen, but instead of Riemann surface and things over C, we are replacing everything over Q, and the map will be of algebraic curves over Q. There exists some integer n greater than 0. Then for some integer n greater than 0, there exists a surjective morphism over Q of algebraic curves. So basically this is a morphism of algebraic curves, and the morphism is actually defined over Q from x naught of n. Now I'm having this algebra or alg subscript to emphasize that this is over Q and it's a curve over Q. So this is like an algebro-geometric version of that complex version of the theorem. Okay, so basically it says that if you have a rational elliptic curve, there is an integer n greater than 0, such that there is a surjective homomorphism or morphism, not homomorphism, surjective morphism of algebraic curves over Q from x naught of n to E. Okay, and then similarly, I can give a Jacobian version, and I can also give an abelian variety version. So let me give them first. So modularity theorem version JQ. So now instead of this, we have like a version over Jacobian. So again, let E be an elliptic curve. Over Q. Then again, for some integer greater than 0, some integer n greater than 0, there exists a surjective homomorphism. Now this is a homomorphism of abelian varieties over Q, or you can, so this is like it's a map of algebraic varieties also, which is defined over Q, and it's also a homomorphism of abelian varieties from J0 of n alg to E. Again, this alg subscript is there just to emphasize that now we are over Q and these are maps over Q and not over C. And then similarly, I can define this modularity theorem version AQ, which is about, which is the same version, but now for these abelian variety quotients of J0. So again, let E be an elliptic curve over Q. Then for some positive integer n and a new form, so the formulation is the same as we had. Then for some integer n greater than 0 and a new form f belonging to so weight 2 and label gamma naught of n, there exists again a surjective homomorphism of abelian varieties over Q. This goes from AF, again I put alg there to emphasize that we are over Q here, to E. Just a second, I need to see if I have seen, yeah, surjectivity is important because a group homomorphism is trivial, right? You can send everything to 0. So we don't want that, that's not the point. So these are like the algebraic versions of the complex versions that we saw, and their equivalence I think can be proven similarly that the way we did it over C. But now it is interesting to know whether the versions over C and Q, how to prove they are equivalent. So let me try to, I'm not going to prove they are equivalent, but I'll tell you now how to give one direction, and the other direction I will just give you a reference because again I'm a bit out of time. But let me just give you a very quick sketch. So version XQ implies version XC. So I should say that this rational versions and the complex versions, they are all equivalent. Okay, that's why they are called versions of the same theorem. It's not as if I'm giving you different theorems. They are all equivalent versions, different versions of the same theorem. So now we are going to see how, if there is a map between algebraic curves, how you get a map between Riemann surfaces. So if E is an elliptic, is a complex elliptic curve, with rational J invariant, then we know that there is there exists a rational elliptic curve E prime, such that E is isomorphic to E prime over C, because we don't know where E is defined, but we do know that it is over C, and E prime is rational. So these are isomorphic over C. Because the J invariant is rational, we can find such a rational elliptic curve E prime. Now this version XQ tells us that this XQ, it gives us a map from x0 of n alg to E prime for some n greater than 0. Because now E prime is and this is over Q, so this map is over Q.
So E is defined over Q if and only if the J invariant belongs to Q?
No, that is not necessarily true, but what is true is that if E has J invariant over Q, then corresponding to that J invariant, there is a rational elliptic curve. And because they have the same J invariants, they are isomorphic.
They are isomorphic, no?
Yeah.
So that E is also defined over Q?
No, not necessarily, right? The isomorphism could not be over Q, it could be over C.
Isomorphism, no, but I mean, yeah, the isomorphism may not be defined over Q.
Yeah.
But E has a structure, underlying structure that is defined over Q.
I'm not sure because the E could have an equation which is not over Q, right? I mean, this isomorphism.
He has an equation with complex coefficients,
Right.
but J is in Q.
Yes.
Then are you saying that he also has an equation defined over Q?
No, I'm not saying that. I'm just saying that there is an E prime whose equation is defined over Q, such that
Yes.
isomorphic to E prime over C.
Yeah, but I think you're saying then that E has also the equation.
No, I'm not saying. I mean, I'm just saying that they are isomorphic over C. I don't know if it can have an equation over.
Look, the isomorphism may be over C. The setup is there, but E and E prime are the same, and so he has a structure. He has a Q structure.
Not really. I mean, basically, for this isomorphism, see, basically the theorem, the result that I'm using is that if I have two elliptic curves defined over a field K, and their J invariants are the same, then they're isomorphic over K. So for E prime, my K is Q, but I don't know if E is over Q or not. But E and E prime both are over C. So I'm sort of applying this theorem over C. So this is a slightly a weird thing. I'm not sure if E can be defined over Q.
I think what he meant is you can identify E and E prime as compact Riemann surfaces because they are isomorphic over C.
Right.
So then you can just identify E and E prime as compact Riemann surfaces, and then one of them is defined over Q. So other, I mean,
no, but it's not obvious. Like I don't see how you go.
Isomorphism could be over Q bar.
Yeah, he can. Yeah. I think you can still say that E is over Q bar maybe, but not over Q. I don't know. Anyway, continuing. So we have this map from x naught of Walsh to E prime. So we go to the C points. So extending it to C points gives us a map from between C points, x naught of n Walsh C to E prime of C, but we know that E prime of C is isomorphic to E of C because E and E prime are isomorphic over C. So this means we get a map of Riemann surfaces. Map of Riemann surfaces. Some more justification is, I think, required here, but unfortunately, I'm out of time, so I'm going to skip it. But we get a map of Riemann surfaces because we have a map on complex points, which is coming from Q. And the other version is, in fact, even more difficult. Version XC implying version XQ. This is a bit more difficult because, so I'll give you a reference. The reference is appendix to Mazur's beautifully written article, Number Theory as Gadfly. Number Theory as Gadfly. It's a very good article, and in the appendix he gives this theorem, but it involves some previous results of Shimura and some arguments which are not really straightforward. I mean, it could be explained, but not in like 2 minutes, unfortunately.
Someone else will talk about it in detail.
Sorry?
Someone else will talk about this in detail.
Right. So I would just say one thing, it uses this decomposition of J naught of n into abelian varieties that we saw above. So it uses this very crucially. So basically, the moral of the story is that we have some versions over C and we have some versions over Q, and they're all equivalent. But there is still the connection with modular forms is still slightly missing. So I'm going to give you a version which gives you connection with modular forms. Because, okay, you still have this abelian variety coming from modular form, so you are very happy, and you can say that okay, that's a connection, but there is a bit more explicit connection which I would like to say. So this is going to be the end of my talk where I will give you this connection. So to do that, let E be an elliptic curve, a rational elliptic curve. And E prime be the integral model of E. So basically we are just modifying the equation of E to have coefficients over Z, and with global minimal Weierstrass equation, which means the equation is minimal for all primes P. So it means the Weierstrass equation is minimal for all primes P. This exists. So now this E prime is over Z, right? It's a model of E over Z, and it has minimal Weierstrass equation. So I can reduce E prime modulo P for every prime P. So let for a prime P, let E bar P be reduction of E prime modulo P. Because the equation is over Z, we can reduce it modulo P. So E bar of P is an elliptic curve if and only if this is a prime of good reduction. P is a prime of good reduction. So for all but finitely many primes, this is an elliptic curve, but not always. And now I define AP of E to be defined to be P plus 1 minus the number of points of this E bar of P over FP. Okay, so if this is not an elliptic curve, this is easy to count. But if it is an elliptic curve, then this is not so easy to count. And now what the modularity theorem, the next version I'm going to state, it says that this AP of E, they appear as Fourier coefficients or Hecke eigenvalues of a new form of certain level.
Oh, wow.
So this information AP of E is encoded in a weight 2 modular form. This is the the next the version that I'm going to state, and Diamond-Schulman calls it version AP. So I should have said that I'm following Diamond-Schulman here all the time. Modularity theorem version AP, it says that let E be an elliptic curve over Q. And let its conductor be NE. So this NE means conductor is basically it has the information of which primes are of bad reduction and how bad the reduction is. Depending on that, we know what power of prime divides NE. Then there exists a new form F of level S2 of gamma naught of NE. So it has weight 2 level NE, and it's a new form. That AP of F is AP of E for all primes P. So this AP of F is a TP eigenvalue of F. So if F is normalized, then this is just the pth Fourier coefficient of F, and this is telling you that there is a new form of level NE and weight 2, such that the Fourier coefficients, they are telling you this information about the number of points of this elliptic curves when you reduce it modulo P. Or if you want to know, if you want to write it in terms of L function, as we must have seen in the lecture of Professor Winnie Lee, this means that the L function of F is same as the L function of E. And I would like to also mention a fact that basically, so this means that this modular form F has eigenvalues in Q, right? Has Hecke eigenvalues in Q. That is because APF are these are all the Hecke. These are the eigenvalues which generate all the Hecke eigenvalues, and that is equal to AP of A, which is an integer. It's a number. So AP of F are rational. So sorry. So these are the Hecke eigenvalues in Q, which means KE. Sorry, that means the KF. The coefficient field is Q. Kf is Q. And basically one can prove that in this case, once you know that there is such an eigenform, we have a surjective homomorphism of abelian varieties from AF, the quotient of Jacobian given by this F, to E. But AF, this has dimension equal to the degree, which is 1. So this means that AF is an elliptic curve. And map is an isogeny. This map is an isogeny. So this means, basically this means that so the statement sort of says that, so modularity theorem says that every elliptic curve is isogenous to AF for some F belonging to S2 of gamma naught of N with rational Fourier coefficients. So basically, whenever you have an F, which is an eigenform with rational Fourier coefficient, this AF is an elliptic curve. And the modularity theorem says that any elliptic curve is basically isogenous to such an elliptic curve. That's why the first statement, which I stated, that every elliptic curve arises from a modular form. And this is what it means, that you take every rational elliptic curve arises from a modular form. This is what I meant, that you take an elliptic curve which is over rational numbers. Then there is a modular form F, new form F of weight 2, such that the corresponding abelian variety is an elliptic curve which is isogenous to your given elliptic curve. Okay, so this is the sort of the modular form version of this modularity theorem. I'm out of time, and anyway, the proof is not that easy. You have to use these Eichler-Shimura relations and so on. You can see a partial proof in Diamond-Schulman. But since I'm out of time, I'm going to stop here. Thank you.
So let us thank Shaunak for the wonderful talk. So are there any questions or comments?
So any comment about this last version that you stated and that XE version, XQ version, briefly?
So let me just go back. So this version, right?
This version and XQ version.
Yeah, so a small comment that I would like to make is that, whenever you get these modular forms, you have to sort of go via Jacobians. So once you go via Jacobians, you have to sort of look at the various map between Jacobians you get, and you have to use Eichler-Shimura a bit. I mean, there's no short way of saying this, unfortunately. I'm trying to think, but you have this splitting of Jacobian into abelian varieties. And then you have maps between Jacobians given by Hecke operators. And then you can also look at them as maps between abelian varieties. And if this APF and APE, they are not matching, that means if you look at this operator TP minus APE, which makes sense, APE is an integer. So then this operator sort of becomes, this map sort of becomes surjective if this equality is not going to hold. But then you can bring in your Eichler-Shimura relations to get some sort of a contradiction to the fact that there is a surjective map from J0 of N, things like that. So rather than connecting it directly with the XQ version, you sort of connect it with the JQ version, because JQ version is more intimately related with modular forms. And then switching between JQ and XQ is not that hard. Does it at least answer your to some extent? Yeah.
Have you by chance looked at an old book by H.F. Baker on Abel's theorem?
No, I did not get time to look at it. I've heard of it.
No, it's a very old book.
Yeah.
But I mean, it doesn't have any of this, but it has many instances of the splitting of the Jacobian into elliptic, into abelian varieties.
Abelian varieties, yeah. No, I've heard of the book, and this kind of thing, it is used a lot. The splitting of Jacobian into these abelian varieties. This has a lot of arithmetic applications.
Yes.
Used very widely. So it's an important theme. I went over it very quickly, but I'd like to stress that the splitting is very important and crucial.
There are many explicit formulas there.
Yes.
The Klein's quartic.
Mm-hmm.
I think the Jacobian of that is, I think, splits like this. I think.
I see. Okay. Interesting. I did not know this.
Yeah, I'm not sure. I mean,
Yeah, sure. I can check it out. Yeah.
Whether it splits into 3 factors or 2 factors, I don't know.
I see. Okay. Interesting.
But a curve with many symmetries tends to be something with the splitting of Jacobians.
Right.
I want to clarify one thing.
Yes.
So this last version you stated is also equivalent to all earlier versions, right?
Yes, it is equivalent to all earlier versions. Yes.
So then if you go back to version in which you mentioned this abelian variety AF,
Yes.
that should be elliptic curve. Because it has rational Fourier coefficients in the last version.
So here you mean?
Yes.
Yeah. So yeah, eventually it will turn out to be an elliptic curve because of this AP. But a priori.
Okay, a priori we only say it's a number field KF, but eventually it is.
Yeah, eventually it becomes. But basically, in your splitting of J naught of n, you have some modular forms which are not rational, and then you get some abelian varieties.
No, sorry, say it again.
In your splitting of Jacobian, you get some abelian varieties which are not elliptic curves because all the f may not be rational.
Yeah, but if once you show that it is equivalent to the last statement that you stated, then they will come out to be rational.
No, so basically the statement is saying that given an elliptic curve, there exists an f, but the statement is not saying given an f, there is an elliptic curve.
But no, those two f's are same, right? The f's appearing in one version is same as the f appearing in the last.
Yes. So the AF appearing in this version is elliptic curve. I agree. I'm saying to look at the splitting of Jacobian, the AFs may not be elliptic curves.
That is okay.
Yeah. But yeah, this AF, it is elliptic curve, that I agree. Once you know that this is equivalent to the other version, we know that this is an elliptic curve. Yes.
And that would also, that multiplicity one theorem would say that this F is unique, and so.
Yes. Some sort of multiplicity theorem will say that. Yes.
Okay. Yeah. Thanks.
So there are some generalization of this theorem, like Jack Thorne has a very short proof that elliptic curve over cyclotomic ZP extension of Q are modular.
Yes.
Then this 6sec and all this for real quadratic field. What is the the most state of the art result on this?
Yeah, good question. Unfortunately, I forgot to check this, but I can say that a lot of progress has been happening. I think right now, maybe real fields are totally real fields. Maybe we know more, but this quadratic imaginary and CM field seems to be like the sticky cases. So this famous 10-author paper, I think it tries to do this CM case, and I think that they prove it for imaginary quadratic. That I know for sure, I think. And then there is also this paper of Calgary, G, Boxer, and Piloni. Tries to prove this sort of things for maybe abelian surfaces. I have not checked. It's like a 300-page paper. I should have checked, but I have not checked the latest, the latest thing about modularity over number fields. But the impression I have is that totally real, we do know some things, and obviously Jack Thorne has proven for cyclotomic extensions. But for imaginary quadratic fields and CM fields, the state was very bad till now. But with this new 10-author paper and new things, I think we know some things about that as well. But maybe the CM case is more mysterious than totally real. I mean, both are mysterious, but maybe CM is more mysterious.
Yeah, thanks a lot. So are there any other questions? So this written notes will be available, Shaunak?
Yeah, I will send. I'll make a PDF and will send it to Devendra, and then they will be available on the web page.
Right. Great. So let us thank Shaunak for these two wonderful talks and
Thank you.
very beautifully presented. And these notes will be available in the website. So,
Thank you.
Thanks,
Thank you.
Somnath, for sharing also.
thank you. Thank you, everyone.
Very good talk. Very good talk.
Okay.
Thanks,
So,
Somnath. Maybe see you again sometime.
yes, sir. Nice to see
Stop
you.
presenting.
Yeah. So,
Ganesh, you can maybe stop the live streaming and other things.
good.
So there is some Galva version also, right?
Galva version in the sense.
Galva representation version.
Oh yeah. Oh sorry, I forgot to state that. Yes, the Galva representation version basically states that if you have the elliptic curve over rational numbers, then the Galva representation attached to it, elliptic Galva representation, is same as the elliptic Galva representation attached to a weight 2 new form.
But how does it relate to these geometric versions?
Yeah, so it doesn't relate to the geometric version per se, but this AP version, this APF is APE, you got this, right? And these APs, they are trace of the Frobenius for the Galva representations.
Okay.
So it is telling you that the trace of the Frobenius is matching at a dense set, because Chebotarev says that these elements whose traces are APs, they are dense.
I see.
So that's how you get this irreducibility will tell you that they are the same. It's basically, this is a very short version of the proof. In I think chapter 9 of Diamond Schurman, he does it.
Okay. Okay, thanks.
Thank you.
Yeah. So great to have you, Shaunak, and see you all of you around sometime.
Sure. Yeah, see you around. Thank you. And thanks for the invitation.
Yeah. Ganesh, are you stopping the live stream?
See you around.
See you, bye.
Bye.
हाँ बंद करो ना इसको लाइव स्ट्रीम बंद करो सबसे पहले फिर रिकॉर्डिंग मीटिंग
So you understand this live stream and also
Yeah.
the
once or twice I have